In model theory, a transfer principle states that all statements of some language that are true for some structure are true for another structure. One of the first examples was the Lefschetz principle, stating that any sentence in the first-order language of fields true for the complex numbers is also true for any algebraically closed field of characteristic 0. History. An incipient form of a transfer principle was described by Leibniz under the name of the law of continuity. Here infinitesimals are expected to have the same properties as appreciable numbers. Similar tendencies are found in Cauchy, who used infinitesimals to define both the continuity of functions and a form of the Dirac delta function. In 1955, Jerzy proved the transfer principle for any hyperreal number system. Its most common use is in Abraham Robinson's non-standard analysis of the hyperreal numbers, where the transfer principle states that any sentence expressible in a certain formal language that is true of real numbers is also true of hyperreal numbers. Transfer principle for the hyperreals. The transfer principle concerns the logical relation between the properties of the real numbers R and the properties of a larger field denoted *R called the hyperreals. The field *R includes, in particular, infinitesimal numbers, providing a rigorous mathematical realization of a project initiated by Leibniz. The idea is to express analysis over R in a suitable language of mathematical logic, and then point out that this language applies equally well to *R. This turns out to be possible because at the set theoretic level, the propositions in such a language are interpreted to apply only to internal sets rather than to all sets. As Robinson put it, the sentences of the theory are interpreted in *R in Henkin's sense. The theorem to the effect that each proposition valid over R is also valid over *R is called the transfer principle. There are several different versions of the transfer principle, depending on what model of non-standard mathematics is being used. In terms of model theory, the transfer principle states that a map from a standard model to a non-standard model is an elementary embedding, or sometimes a bounded elementary embedding. The transfer principle appears to lead to contradictions if it is not handled correctly. For example, since the hyperreal numbers form a non-Archimedean ordered field and the reals form an Archimedean ordered field, the property of being Archimedean seems at first sight not to satisfy the transfer principle. The statement, every positive hyperreal is larger than 1, and for some positive integer n, is false. However, the correct interpretation is, every positive hyperreal is larger than 1, and for some positive hyperinteger n. In other words, the hyperreals appear to be Archimedean to an internal observer living in the non-standard universe, but appear to be non-Archimedean to an external observer outside the universe. A freshman-level accessible formulation of the transfer principle is Keisler's book Elementary Calculus, an infinitesimal approach. Example: every real x satisfies the inequality where x is the integer part function. By a typical application of the transfer principle, every hyperreal x satisfies the inequality where asterisk is the natural extension of the integer part function. If x is infinite, then the hyperinteger asterisk x is infinite as well. Generalizations of the concept of number. Historically, the concept of number has been repeatedly generalized. The addition of 0 to the natural numbers was a major intellectual accomplishment in its time. The further extension, the rational numbers, is more familiar to a layperson than the completion, partly because the rails do not correspond to any physical reality different from that represented by. Thus, the notion of an irrational number is meaningless to even the most powerful floating-point computer. The necessity for such an extension stems not from physical observation but rather from the internal requirements of mathematical coherence. The infinitesimals entered mathematical discourse at a time when such a notion was required by mathematical developments at the time, namely the emergence of what became known as the infinitesimal calculus. As already mentioned above, the mathematical justification for this latest extension was delayed by 3 centuries. Keisler wrote, "In discussing the real line we remarked that we have no way of knowing what a line in physical space is really like. It might be like the hyperreal line, the real line, or neither. However, in applications of the calculus, it is helpful to imagine a line in physical space as a hyperreal line. The self-consistent development of the hyperreals turned out to be possible if every true first-order logic statement that uses basic arithmetic and quantifies only over the real numbers was assumed to be true in a reinterpreted form if we presume that it quantifies over hyperreal numbers. For example, we can state that for every real number there is another number greater than it. The same will then also hold for hyperreals. Another example is the statement that if you add 1 to a number you get a bigger number, which will also hold for hyperreals. The correct general statement that formulates these equivalences is called the transfer principle. Note that in many formulas in analysis quantification is over higher-order objects such as functions and sets, which makes the transfer principle somewhat more subtle than the above examples suggest. Differences between R and *R. The transfer principle, however, doesn't mean that R and *R have identical behavior. For instance, in *R there exists an element omega such that, but there is no such number in R. This is possible because the non-existence of this number cannot be expressed as a first-order statement of the above type. A hyperreal number like omega is called infinitely large. The reciprocals of the infinitely large numbers are the infinitesimals. The hyperreals *R form an ordered field containing the rails R as a subfield. Unlike the rails, the hyperreals do not form a standard metric space, but by virtue of their order they carry an order topology. Constructions of the hyperreals. The hyperreals can be developed either axiomatically or by more constructively oriented methods. The essence of the axiomatic approach is to assert the existence of at least one infinitesimal number, and the validity of the transfer principle. In the following subsection we give a detailed outline of a more constructive approach. This method allows one to construct the hyperreals if given a set theoretic object called an ultrafilter, but the ultrafilter itself cannot be explicitly constructed. Vladimir Konovet and Scheller give a construction of a definable, countably saturated elementary extension of the structure consisting of the rails and all finitary relations on it. In its most general form, transfer is a bounded elementary embedding between structures. Statement: the ordered field *R of non-standard real numbers properly includes the real field R. Like all ordered fields that properly include R, this field is non-Archimedean. It means that some members x0 of *R are infinitesimal, i.e., the only infinitesimal in R is 0. Some other members of *R, the reciprocals y of the non-zero infinitesimals, are infinite, i.e., the underlying set of the field *R is the image of R under a mapping A*K from subsets A of R to subsets of *R, in every case with equality if and only if A is finite. Sets of the form *K for some are called standard subsets of *R. The standard sets belong to a much larger class of subsets of *R called internal sets. Similarly, each function extends to a function. These are called standard functions, and belong to the much larger class of internal functions. Sets and functions that are not internal or external. The importance of these concepts stems from their role in the following proposition and is illustrated by the examples that follow it. The transfer principle. Suppose a proposition that is true of *R can be expressed via functions of finitely many variables x plus y, relations among finitely many variables, finitary logical connectives such as and, or, not, if, then, and the quantifiers. Suppose a proposition otherwise expressible as simply as those considered above mentions some particular sets. Such a proposition is true in R if and only if it is true in *R with each such a replaced by the corresponding *A. Here are two examples. The set must be including not only members of R between 0 and 1 inclusive but also members of *R between 0 and 1 that differ from those by infinitesimals. To see this, observe that the sentence is true in R, and apply the transfer principle. The set *n must have no upper bound in *R and must contain n+1 if it contains n, but must not contain anything between n and n+1. Members if R infinite integers. Suppose a proposition otherwise expressible as simply as those considered above contains the quantifier. Such a proposition is true in R if and only if it is true in *R after the changes specified above and the replacement of the quantifiers with an. 3 examples. The appropriate setting for the hyperreal transfer principle is the world of internal entities. Thus, the well-ordering property of the natural numbers by transfer yields the fact that every internal subset of has a least element. In this section, internal sets are discussed in more detail. Every non-empty internal subset of *R that has an upper bound in *R has a least upper bound in *R. Consequently, the set of all infinitesimals is external. The well-ordering principle implies every non-empty internal subset of *n has a smallest member. Consequently, the set of all infinite integers is external. If n is an infinite integer, then the set 1, n, must be internal. To prove this, first observe that the following is trivially true. Consequently, as with internal sets, so with internal functions. Replace with when applying the transfer principle, and similarly with in place if. For example, if n is an infinite integer, then the complement of the image of any internal one-to-one function f from the infinite set 1, n, into 1, n, n plus 1, n plus 2, n plus 3, has exactly 3 members by the transfer principle. Because of the infiniteness of the domain, the complements of the images of one-to-one functions from the former set to the latter come in many sizes, but most of these functions are external. This last example motivates an important definition. A * finite subset of *R is one that can be placed in internal one-to-one correspondence with 1, n, for some n *n.